So it gives me great pleasure to welcome Nisarg back. This is actually his third time visiting Ithaca. I've been trying to get him over for a while. I've been working with Nisarg for a while on and off and trying to get him over. He's pretty close by in Toronto, but we finally figured out a time to get him to drive down. So Nisarg has been doing a set of amazing projects in the intersection of fairness and various societal constraints in AI and in decision making. I first actually learned about his work when actually back in 2015, his advisor, Ariel Procaccia, was working on problems in fairness, and he was creating this website called Split It. And the idea was we do all of this stuff in theory. We want people to actually use fair division in practice. So let's create a website and people will come. And if you had asked me at that time to have a bet as to whether anyone would use it, I would have definitely said no one would. But I did not at that point know anything about Nisarg, and I did not know how much work he would be actually putting into the website. And it's actually been a remarkable success. I don't know how many of you have seen Split It, but like people all over the world actually use this website for a variety of problems. And there's an interesting side effect of this, which I remember Nisarg talking about, that people would actually write to Nisarg and his collaborators saying, hey, we have this fair division problem, can you solve it for us? And then they would go and solve it in practice, but also write a paper about it. And so many of us struggle to figure new problems to work on. Maybe we should create a website and have people suggest it to us. So since then, he's been at the University of Toronto. He's won a variety of awards. But what's even more remarkable, and I think you'll see this in this talk, so many of us, when we think about what work we do, we either say something like, okay, we work in theory. So we work on sort of the cutting edge of like these theoretical problems, or we work on theory inspired by application, or maybe we work on applied problems with some theoretical guarantees, or maybe we do purely applied things which actually touch people. Nisarg is one of the few people I know who can answer yes to all of those questions. He literally does work on each of these, and I think you'll see some of that in the work that he will present today. So without further ado, over to you.
Thank you, Sid, for that very generous introduction, more generous than I would have ever given myself. So thank you all for coming. Great to see such a big turnout for an in-person seminar. And thank you for all the people who were able to join through Zoom. So as Sid said, I'm at the University of Toronto. Just some kind of credit to a bunch of institutes that I'm affiliated with at the University of Toronto, which have been very crucial for helping me conduct some of the research that I've been doing, especially along the lines of algorithmic fairness. And so the topic of today's talk is going to be designing optimal voting rules. So this is an agenda or a paradigm of rethinking how we should design voting rules, how we should conduct voting in practice from a very different perspective than how it has been thought about for centuries now. And there are some reasons why I like this paradigm better than some of the previous paradigms that I also personally worked on for many years. And so I'll try to give you a glimpse of a bunch of results that we have had along the last few years, trying to find out the so-called best voting rules according to this paradigm, and then what those voting rules look like, what kind of guarantees those voting rules provide to us, and why we should maybe consider using some of those voting rules in practice. All right, so just before I get into the technical work, so credit to my excellent collaborators. So primarily this talk is going to be based on 4 or 5 papers, which are done with different groups of collaborators. So Surush and Mohammed are my PhD students currently. Anson is one of my postdocs. Dominic was an ex-postdoc who recently left and started his faculty position in CNRS. Daniel Halpern was an undergraduate student at University of Toronto, now a PhD student at Harvard. And Alan Borodin is a faculty member at U of T, who I work with. Dharmalya Mandal was a postdoc as a PhD student at Harvard, where I did my postdoc. David Woodruff is a faculty member at CMU, and Ariel Procaccia was my PhD supervisor. So voting or voting rule is simply an algorithm that collects the individual preferences about some problem, something that we are trying to decide on, and then informs us on how to make some collective decisions that balance the preferences of these different individuals. And there are various problems in which voting can be applied. When I talk about voting, the one application that most people immediately think about is political elections, right? So this is where we use voting most frequently in the real world. At least that's what we think. This is where voting comes up at least the most when we talk about voting, when we discuss how voting should be conducted, how voting should work. But as I go through this talk, one thing that I want you to keep in mind is that this is not the only context in which we use voting in the real world. In fact, this is there are other contexts where we use voting much more frequently than in political elections. For example, every time a group of friends are trying to discuss where they should go for lunch, really what goes on is some kind of voting procedure. It may not be an explicit voting procedure where they submit their preferences to some kind of algorithm and then the algorithm makes the decisions for them. But you could, at least in principle, think about replacing this decision-making process by an algorithm if we think that algorithm would make these decisions more efficiently in the long run for this group of people. Okay, so these are the one thing that's kind of different in these applications than the political decision application is that the political decision application is a very high-stake application, right? So any decision that you are making, it has a significant impact, which means that you do not want to make a decision that seems maybe not that good, even with a tiny probability, right? You really don't want to take any risk. What you want to do is you want to use a deterministic voting rule, one that chooses the option that seems the most appealing based on what information you are able to see, and you want to just go with that alternative or that option with probability 1. Okay, and you don't want to take any risk. But I want to kind of try to convince you that that's not always true in all these other applications of voting. In applications that are very low stakes, such as deciding where to go for lunch or deciding which book to read in a book club, these are low stakes applications and applications that are repeated quite often, that it makes sense to take some amount of risk if that hedges your risk well, and in long run, you are going to make more efficient decisions on average. And so in these kind of contexts, probabilistic voting rules make a lot of sense. You maybe want to choose between the different available options with different probabilities based on how appealing those options seem, or based on what is the kind of the probability with which those options can turn out to be optimal in hindsight. Right. So another application is recommendation systems. So recommendation systems that make recommendations to incoming users by combining the recommendations given by different classifiers. So think of an ensemble learning approach to those of you who are familiar with some machine learning methodologies. This is another case where soft classifications or randomized decisions are often deployed. Another application is budget division. So think about a city trying to divide its budget between the different sectors like education sector, healthcare, transportation, infrastructure, etc., based on the preferences of its residents. This is actually something that some of the cities have started doing recently. And this is where you again want to deploy a probabilistic voting rule, but the interpretation isn't really that the voting rule is probabilistic, it's just that it outputs a fractional division, right? So when you say that I'm going to spend 35% of my budget on infrastructure, it's not really that with 35% probability I'm going to spend all of my money on infrastructure. It's really that I'm just going to spend 35% of my budget on infrastructure. So during the talk, when I talk about probabilistic voting rule, it would be equivalent to thinking about fractional voting rules, which output a distribution or a budget allocation. Yeah, so it could actually be a deterministic voting rule that outputs a fractional outcome. All right, so the canonical model in which voting has been studied for many, many centuries is that you have a number of voters. These are denoted in black. You have a number of candidates, say the red, green, and blue candidates. And each voter ranks the different candidates based on how much they like them. And then they submit this information to some voting rule, which aggregates all of this information to pick a winning candidate, once again, either deterministically or in a randomized fashion. And people have thought about how to design the optimal voting rule in these kind of settings for many centuries. And one of the approaches that has been investigated a whole lot by mathematicians, philosophers, economists over the many centuries is this so-called axiomatic approach, where you define some qualitative axioms, some properties that you want your voting rules to satisfy, and then you try to find voting rules that satisfy maybe many of these appealing properties at the same time. And the hope here is that by defining some reasonable properties and then trying to see voting rules that lie in the intersection of those properties, you will find a unique voting rule satisfies all of these properties at the same time. But more often than not, when you define these reasonable axioms, what you find is an impossibility result, like the arrow's impossibility result to those of you who may have heard of it, that you cannot satisfy these reasonable axioms at the same time. And people have, over the centuries, people have thought about many different properties. So this is actually a snapshot from a Wikipedia page about voting. People have defined many different properties that you may want to satisfy, many different voting rules that make sense, and then figured out whether or not these voting rules satisfy these different properties. But there is no clear consensus as to which voting rule we should actually use in practice based on all of this information. So one thing that I've started working on recently is a very different approach to thinking about voting, which stemmed from a paper in computer science back in 2006. And what this paper says is that we still have this canonical model of voting, but now we imagine that when each voter is ranking the different candidates, the voter actually has some underlying intensities of preferences that the voter is not telling us about. So what do I mean by that? When this voter here ranks the red candidate above the green candidate above the blue candidate, we know that this voter likes the red candidate at least as much as the green candidate, which is at least as much as the blue candidate, but we don't know how much more. Maybe they like the three candidates in the ratio of 7:2:1. Maybe they like the three candidates in the ratio of 1:1:1, which means that they really like them equally and they just broke the ties arbitrarily. Or maybe they like them in the ratio of 3:2:1. Who is to tell? Right? And so what this approach says is that any intensity of these preferences, you can convert them into an underlying numerical utility function that this voter has. And to keep the voters on equal footing, we are going to assume that these utility functions are normalized to sum up to 1. So if the voter likes the three candidates in the ratio of 7:2:1, then I'm just going to say that this voter has utility 0.7 for the red candidate, 0.2 for the green candidate, and 0.1 for the blue candidate. Right? But I don't really know this utility function. This voter could have this utility function, but infinitely many other utility functions as well. All I know is that her utility for the red candidate is at least as much as her utility for the green candidate, which is at least as much as her utility for the blue candidate, and they sum up to 1. All right. So what does this approach actually get us? Well, when we were just thinking about aggregating these rank preferences, there was no clear answer as to what we should even aim for. Right? When you are aggregating rankings, there are no well-defined, agreed upon objective functions or principles that people know how to follow. But when you are working with these underlying numerical utility functions, even if you don't really know what these utility functions are, what you can say is that if I knew these utility functions, then there are some reasonably well-agreed objective functions that one would try to optimize. One of them is the utilitarian social welfare, which is very well justified as a form of efficiency in the utilitarianism theory of Bentham. So if I knew these utility functions, this exact numerical intensity of preferences, then what I would do is I would compute the total utility that each candidate gives to all the voters, the total happiness that it generates in the society, and I would want to pick the candidate that has the highest social welfare. But because I don't really know these numerical intensities, my voting rule will aggregate this information and it may end up selecting a different candidate. That's fine. All I need to do is look at how far this candidate is from the one that actually maximizes social welfare. And one way to do this is to look at the approximation ratio that this candidate achieves to maximizing social welfare. And this is simply the maximum possible social welfare that I could have achieved divided by the social welfare of this candidate. But this ratio is only for this particular underlying case. Of course, this is not the only case I need to worry about.
there are infinitely many possible underlying utility functions that could exist given these rank preferences. So I need to take the worst case ratio over all possible underlying preferences. And this is exactly what distortion is. For some reason in this literature, it is this worst case approximation ratio of social welfare is termed distortion. And the idea is that each voting rule now has a number assigned to it, a single number, which is its worst case approximation ratio, and we should seek the voting rule that minimizes this number, and we should deploy that voting rule in practice, at least if efficiency is what we care about. Okay? Later in the talk, I'll talk about fairness and some other things that you might want to care about, and then you would seek other voting rules. All right, so just some brief notation so that we are all on the same page, but feel free to not pay too much attention to this notation. So I'll use capital N as a set of N voters, capital A as a set of M alternatives, and then I'll use a sigma vector as the observed ranked preference profile, which contains the ranking provided by each voter, the U vector as the underlying utility profile, which is the underlying utility functions of the different voters, which I don't really know. All I know is that for every voter, her utility function ui is consistent with the reported ranking sigma I. So her utilities are non-increasing in that order, and her utilities sum up to 1. Beyond that, I don't really know anything about these utility functions. And once I have the utilities for the different individual alternatives, I can also define the utilities for distributions over alternatives by simply taking the expected utilities. Yeah, but this is only if you are in the probabilistic setting. If you are in something like the budget allocation setting, then this can be thought of as linear utilities. And then you can define the social welfare as simply the sum of the utilities that that distribution generates in the society. And then the idea is that we want to look at the distortion, which is some kind of goodness of fit that this distribution has for this particular rank preference profile that is given to us as input. And that is simply the worst case or supremum over all possible utility profiles that could be consistent with the observed rank preference profile, the approximation ratio of the social welfare that we achieve, which is the ratio between the maximum social welfare we could have achieved by picking the right candidate which maximizes the social welfare, divided by the social welfare of the outcome or the distribution that we actually picked on this profile. And given a voting rule F, we assign to it a single number, which is called the distortion of this voting rule, which is simply the worst case over all possible inputs that the voting rule could ever receive, the distortion that its output has on that input. So this is what we want to minimize, and we want to find the voting rule F that has the smallest distortion. And one note that I want to make here before moving on is that there is actually a very interesting structure about this problem. You can find a voting rule that doesn't just have a best distortion in the worst case over all possible inputs. You can actually find a golden rule that has instance by instance best possible answer. So for every preference profile sigma vector that you can take as input, you can find the x that minimizes this quantity, and that particular outcome is the best possible outcome on that particular input. Yes?
So I think I understand why you're taking the supremum over the U. It's going to have some nice properties. But from a practical perspective, I guess, could you say something about that?
Yes, very nice. So just for people on Zoom, if you weren't able to hear it, the question is, I'm taking the supremum over U here, which is basically a worst case approach or a pessimistic approach. I want to make sure that no matter what these utility functions are, this alternative still is a reasonable approximation of the social welfare. But in practice, maybe not all these utility functions can arise, at least not with equal probability. So what if I take some kind of like empirical average or some kind of distribution over the utility functions? Now, in this literature, one thing that people try to do is they try to avoid some subjective assumptions. Now, in some sense, the worst case is also a subjective assumption. But then if you want to replace this worst case, the natural thing to do is to do some kind of average case. But then you have to specify a particular probability distribution over the possible utility profiles that you can have consistent with the observed rank profile. Now you can say all possible utility profiles that are consistent with the observed rank profile are equally likely. So I'm just going to optimize the uniform distribution over the possible underlying information. But that's kind of one subjective assumption, and then people try to avoid that. The other answer to this question is that let's first try to optimize for the worst case and see how bad that worst case actually is. Even that worst case, if that's not actually that bad, then we are in good hands. Right? If I can actually get a good approximation of the social welfare, even in the worst case, then maybe there is less reason to try and shoot for the average case. And that's what I'll actually try to convince you that that's what happens in this problem. All right. Any questions before we move on? So what was known about this problem? Well, for deterministic voting rules, situation is pretty bad. The distortion of every deterministic voting rule is as bad as square of the number of candidates. There's a technical reason why it does not depend on the number of voters. Both the numerator and the denominator here scale linearly with the number of voters because you are summing up the utilities of all the voters. So the number of voters kind of cancels out from both cases. So the distortion almost always ends up becoming a function of just the number of candidates, which is a good thing because the number of voters typically is much larger than the number of candidates, at least in the political applications. All right, so the distortion of every deterministic voting rule is pretty bad. It's the square of the number of candidates. And the best distortion is already achieved by one of the simplest voting rules called plurality, where each person just kind of votes for their most favorite candidate, and the person who receives the most votes wins the election. And this can kind of be surprising that we have all this ranked preference information. Why should we throw away all of this ranked preference information and just focus on the top choice votes? Well, the problem here is that kind of if you care about the worst case, and this is where kind of I think something like the average case would be much better. If you care about the worst case, in case of deterministic rules, it really biases you to only think about the top choice votes. Because then people can end up having these utilities that are 1 for the top choice vote and 0 for everything else. So for example, if you end up choosing an alternative that is not the top choice preference for any of the voters, then this alternative could end up having 0 social welfare, which is pretty bad for you if you are choosing this alternative deterministically. But this is not the case for randomized voting rules. For randomized voting rules, you can choose an alternative with some probability. Even if that is not the top choice of any of the voters, you still have that remaining probability left over to spread between the top choice votes. So it turns out that randomization can actually substantially help for this problem. Boutillier et al. In 2015 showed that every randomized voting rule has distortion at least as bad as square root of the number of candidates, and you can pretty much match that up to a factor that is the iterated logarithm of the number of candidates, which is pretty much constant in real world. All right.
Can I ask you a very
Yes.
basic question in the previous slide? Can you explain what instance optimal rule means? Very basic thing, but I'm missing that.
So the instance optimal rule?
Yeah.
Yeah, so the instance optimal rule is that you don't only kind of, here I'm evaluating each rule based on the worst distortion that it has across all possible inputs, but you can actually define a golden rule that is instance by instance optimal. On every instance, here, it chooses the outcome that is the best for that instance. And so this voting rule clearly has the best distortion in the worst case, but more than that, it has the best approximation of social welfare on every single input at the same time.
So is this rule different from inspecting all candidates and picking the one that gives you least distortion?
Just slightly different in the sense that you want to inspect all possible distributions over candidates and pick the one that gives you the best distortion. That's it. For deterministic rules, it is exactly just inspecting all the candidates and picking the best one, which is why the instance optimal rule for deterministic rules is actually a very simple formula that you can compute in polynomial time. For randomized rules, it turns out that you can still compute the instance optimal rule in polynomial time, but with some interesting linear programming tricks. But so the main result that I want to talk about today is that we remove this Logstar gap. we show that the best distortion that you can get with randomized voting rules is exactly theta of square root m. Now this may not seem like much. Why do I care about this very small Logstar gap that is eliminated now when Logstar is less than 5 for whenever the number of candidates is say the number of atoms in the universe? Then the Logstar of that is 5, so why do I care about this small gap? What I want to convince you is that it's not really the gap that I want you to care about. It's the fact that this approach actually leads to a nicer rule, at least what looks nicer to me, and it has a much, much simpler proof that just works in three very simple steps. So the proof of this square root m Logstar m distortion that was given by Boutillier et al. Was actually a 10-page long proof, whereas the proof of this result is literally just this one definition on this slide, this small proof here, and this small proof here. Okay. I'm not going to walk you through the proof in the interest of time. I did a couple of rehearsals yesterday. I realized that no matter what I do, I cannot walk through that proof in a reasonable amount of time while still showing you a lot of other interesting material. So I'll not walk through that proof, but I just wanted to include that to show that it's a much simpler proof. And but what I can do is I can show you that the rule is much nicer. It relies on much more interesting ideas. All right. So what I'm going to do is I'm going to go through the 3 steps, but skipping the proofs. And in order to show this optimal voting rule, I'm going to first define this so-called idea of stable lotteries. Then I'm going to prove that these kind of stable lotteries always exist. And I'm going to do that by using the minimax theorem. And then I'm going to actually use those stable lotteries to finally define my rule that gets the optimal distortion. Okay, so what are stable lotteries? Imagine that you have this kind of a preference profile where you have 3 voters, and these are the preference rankings that they have over the different candidates. Now I've colored some of the candidates, and these are the only candidates that I want to care about. I don't want to care about the remaining candidates in black. So what are these candidates that I care about? Where there is some set of candidates or alternatives that I care about, some set S, which in this case, let's say, contains the green candidate, the blue candidate, and the yellow candidate. And there is a different candidate, a contestant, that I want to care about, which is, say, the red candidate. And what I want to measure is how many people like this contestant, red candidate, more than every single person in this set S. Okay? So here, if I go through these voters, voter 1 certainly likes the red candidate more than every single person, every other colored candidate. Voter 2, that is not true for voter 2. Right? Voter 2 likes at least one person from this set S more than the red candidate. But this is again true for voter 3. I don't care that this other candidate is in the top position. Voter 3 still likes the red candidate more than every candidate in this set. So given a candidate, and given a set of candidates and a contestant, I can define this quantity V, A, S, which is how many people like this contestant more than everything in this entire set. Now intuitively, the larger this set is, the smaller you want this quantity to be. Because if you are allowed to choose a large set of alternatives, then the number of voters who like some contestant more than everything in your large set of alternatives should be pretty small, if you have selected your large set of alternatives reasonably well. And we say that a distribution over sets of alternatives, so now I'm kind of moving from a set of alternatives to a lottery or a distribution over sets of alternatives, and I say that this distribution over sets of size k is stable if the expected number of people who like any contestant more than the candidates in my set is at most n over k for any contestant A. Okay? So if I kind of try to look for any other alternative A, then the average number of people who would like that A more than all the k candidates that I'm going to choose should be at most n over k. So as I am able to choose more and more candidates, I want the number of people who like any given candidate more than all the k candidates that I'm choosing. I want that number of people to drop linearly in k. And if that happens, I'm going to call this lottery over sets of size k, a stable lottery. This has some connotations with the core property, if you may have heard of it. That is why this kind of terminology is called stable, but I won't get into that for now. Is the definition clear? Yes.
Does the alternative specifically not have to be in S, or does it?
Very good question. So they can be in S. So whenever A is in S, then V of A comma S is just 0. That's actually a great case for me. So if I can kind of hedge my risk so that I can actually include some alternative with a decent probability, that's great for me because that will minimize this quantity quite much. But I will always miss out a given candidate with some probability, and then I will have to care about how many voters like that candidate more than everything that I'm selecting. All right. So the first thing that I want to argue, but I'm not going to argue in this talk, is that for every size k, no matter whether k is 1, 2, or square root m, or log m, or m, for every size k, there is a stable lottery over sets of size k. And this proof is not very, very difficult. It just relies on using the minimax principle and then just using a very simple trick to bound that minimax value. What I want to focus on is how the rule uses this principle. And the rule works as follows. We call this the stable lottery rule. It flips a coin. If the coin turns up heads, then it does the following. It finds a stable lottery over sets of size square root of the number of candidates. Then it samples a set of size square root m from that lottery. And then it just chooses one of the members of this set uniformly at random. So you just kind of take a set from this stable lottery and then choose a member of this set uniformly at random. You do that with probability half. With the remaining probability half, you choose one of the alternatives uniformly at random. This is kind of to hedge the risk of whatever is not covered by this rule over here. And if someone is interested, I can go into more detail as to why this step is required. But note that these probabilities don't have to be half-half. A lot of people really don't like this kind of second part of the rule, which just chooses one of the options uniformly at random. You can reduce this probability from half to any constant, say 0.001. It would still have this O square root m distortion. But also in low stakes settings, I actually claim that something like this could actually be the nice thing to do to explore.
But presumably you pay for that probability in the big O.
Yes,
What's
in the big O,
difference
yes.
On
Yeah, so these,
minus whatever.
correct. So these constants are actually the optimal constants. So if you want to care about the optimal distortion, then, and I claim that at least in low stakes settings, where there is little risk or little that you lose by exploration, this may actually be something that you want to do.
But you didn't answer my question.
Oh, yeah, so you lose, if you change this probability to 0.001, then you lose in the distortion. The distortion goes up from something like 2 square root m to, I think, 200 square root m. Yeah. But the more high stakes your setting is, the more you can kind of adjust this parameter, if you care about something other than the distortion as well. And again, I'm not going to walk through why this rule achieves the square root m distortion, but I want to show you that the proof is very, very short, as opposed to the 10-page long proof for that slightly worse distortion. And at least kind of to my intuitive eye, this rule is also much, much simpler, at least in principle, than the rule that the previous paper had for which was very intricate. All right, so a few thoughts on this rule. One is that this idea of stable lotteries is not new. We did not introduce this. This was actually introduced by a very nice stock paper, I believe, in 2019, which actually showed the existence of a much stronger form of stable lotteries, which don't just bound the number of voters who like a given contestant more than everything that you are picking. They actually bound the number of voters who like at least one of the candidates in some set S prime more than everything from your chosen set S. And they bound this for all possible S prime that is a subset of A, not just singleton S primes. And that actually is not an easy proof. That's a few page long proof, whereas the only case that we need is the case of kind of bounding these singleton deviations, which is a very simple application of Minimax theorem. So this is not really our proof, kind of we just provide this self-contained proof for the special case that we need in the paper. The other idea is that in a follow-up paper, an overlapping set of authors showed that you don't really need these stable lotteries over sets of alternatives. You can actually find a stable set of alternatives, a deterministic set S, such that this V A comma S is bounded not by n over k, but by 16 times n over k. So you can get a 16 approximation of stable committee, and they also show that this 16 cannot be improved to any lower than 2. So you actually cannot always get a stable committee. There are instances where no stable committees exist. And it's an open question whether you can always find whether 2 is the right number. And there is a lot of kind of evidence to believe that it is. So that's an open question for any of you who are interested. Yes?
How easy is it to sample from that stable lottery?
Very good question. So, I think it's coming up right here. So let me just do this point first. I did not talk about the computation part. So how easy is it to compute the stable lottery? How easy is it to sample from the stable lottery? It turns out that we actually all we need to do is solve that minimax game. And even though the space of the stable lottery is all possible kind of distributions over all these combinatorially many sets of alternatives of size k, really, you can solve this minimax lottery approximately. An approximation is kind of good enough for us because this minimax value is at most n over k plus 1 is something what we show, whereas you only need n over k, so you have some room. You can approximate this, and if you use any of the standard methods like multiplicative weights update, then it will actually find a stable lottery that has a very compact representation. It's a distribution over only polynomially many sets of size k, and this whole thing you can compute in polynomial time. So it's not just easy to sample from it, you can actually write down the entire stable lottery in polynomial time if you want to. Alright, so coming back, one thing that I want to highlight is that something that this rule does is something that I haven't seen before in this literature, which is to find a single winner by first choosing a set of winners that is somehow fair. So this stability has been promoted as a notion of fairness, that you are trying to find this set of alternatives that represent the population well. So it first finds a committee of size square root m that somehow represents the population well, and then it chooses one of those square root m alternatives at random. So this whole idea of choosing a single winner by first choosing a fair committee and then choosing one of those members of the fair committee is something novel that may have other applications. And note that our goal here is not fairness in the end, our goal here is welfare approximation in the end, but it's achieved through fairness for committees. Alright, there are some interesting other open questions. The lower bound here is square root m divided by 2. Our upper bound is 2 square root m, so there is some constant factor of 4 that you can still further improve on. And then you can look at other normalizations for utility functions. Maybe the voter utilities shouldn't be normalized to sum up to 1. Maybe they should be normalized so that the max utility that any voter places on any alternative is 1, and the minimum utility that the voter has for any alternative is 0. So that they are kind of contained between this 0 and 1, with the min being 0 and max being 1. This is called the unit range normalization. And it turns out that our stable lottery rule continues to give this order square root m distortion even for unit range utility functions, and in fact for a broader range of utility functions that contains both the unit sum and unit range utilities. But a rule that was introduced by Boutillier et al. In the 2015 paper that achieved a slightly worse distortion of square root of m log m for unit sum utilities, the distortion of that rule actually surprisingly worsens to something like m to the 2/3 for unit range utilities. Alright, so now what I want to do is I want to argue that this stable lottery idea is much more robust than this. So not only does it extend to other forms of normalization, it also extends to other objective functions or other goals that you might have. So one question is, what if your goal is to actually select a committee in the end? Right now we wanted to select a single winner. what if my goal is really to select a committee of size k? But to define the social welfare of a committee of size k, I first need to define what the utility of a single voter I is for a committee of size k. And one of the standard modeling that is used in the literature is that the utility of any voter for any set of alternatives is simply the maximum utility that the voter derives from any alternative in this set. So in some sense, each voter looks towards the one candidate that they relate to the most in this committee that is selected, and they kind of relate to this candidate and derive utility from this candidate. This is not the only sensible model. You can replace this max by the sum or some kind of weighted sum, and people have looked at all these other models as well. One thing that I also want to clarify is that a priori, it is not clear what the distortion of selecting a committee of size k varies as a function of k. Because as you are selecting larger and larger committees, of course you can give voters more and more utilities. But the hindsight optimal, the adversary that knows the utility functions, can also achieve higher and higher social welfare. So it's not clear whether the best worst case approximation of social welfare, whether it increases or decreases as a function of k. And in fact, the best known previous results was from one of my own previous papers with some of the same collaborators back in 2017, where we showed that for deterministic rules, this is the exact formula for how the distortion changes as a function of k. And this is something that starts at the square of the number of candidates, m squared, at k equal to 1. So if you want to select one winner, then the distortion is m squared. If you want to select k equal to m winners, which means you are selecting everything, then the distortion is clearly 1. There's nothing to choose. You're just selecting everything. But for randomized rules, our results were somewhat weak. So we had some nice lower bounds, but our upper bounds were somewhat curious. So the upper bound started by staying at this square root m, but then at some point they increased as a function of k, the size of the committee that you are selecting, and then it decreased as a function of k after some point. And so it wasn't clear from this whether our results are loose or whether there is really this kind of non-monotonicity going on. So, and the largest gap between these lower and upper bounds was something like m to the 1 over 6. So what we showed is that the stable lottery idea actually extends to selecting committees as well. So if your end goal is to select a committee of size k, then you do the following. If the committee that you want to select is small, if it's at most size square root m, then you essentially use the same idea as before, except with probability half, instead of finding a stable committee of size square root m, you now first find a stable committee of size k times square root m, where k is your desired end size. So you basically blow up by a factor of square root m, find a stable committee with this blown up size, select a set from this stable committee, stable lottery, and then subsample from this set of the desired size. And so you always want to blow up by a factor of square root m, but note that this is not, and with probability half, you just choose from all the solutions at random. But note that this kind of blow up is not possible if k is already of size more than square root m. It turns out that that's the regime where the problem is already very easy. You just choose a solution uniformly at random that already works pretty well. If you're already selecting very, very large committees, you don't really need to care, just select something at random. On average, it actually works pretty well. And this gets the optimal distortion, and now we know that at least asymptotically, the distortion stays square root m up to the committee size being equal to square root m, and after that it decreases. It never increases as a function of k, at least not asymptotically. Here is some more evidence for robustness. What if the voters are not providing complete rankings over the alternatives? What if the voters are only ranking their t most favorite alternatives? Say their 10 or 20 most favorite alternatives. It turns out you can just arbitrarily complete the partial preference profile that you are observing. Just fill out the remaining positions in the voters' preferences arbitrarily, and then apply the rule from the previous slide, and that actually works pretty well. And this approach already gets a pretty nice upper bound there's actually some gap here between the upper and the lower bounds. So there's an open question there to close this gap, and we are not sure what part of the rule might be suboptimal. We think that some modification of this, either this weird step where we are just arbitrarily completing any missing information, maybe that part is not really optimal. There's something that we should be able to change such that these two match. But one corollary of this is that if you're back to the regime of choosing a single winner, so remember that for choosing a single winner, if I give you fully ranked ballots, then the optimal distortion is square root m. Turns out that if you only have the top t preferences, then this is what the optimal distortion looks like. And note that at t equal to square root m, it already achieves the optimal distortion of square root m. Which means that if you are only asking each voter to provide a ranking over their top square root m most favorite candidates, that's already enough to get the best possible approximation of social welfare. There is really no point to asking the voters of ranking any more candidates. So if you are trying to truncate the ballots in order to make it easier for the voters, truncate the ballots at the size square root m. Right. Some visualization that we have in the paper for showing where the gaps are. Okay, and the final thing that I want to focus on in today's talk is that you can further extend this idea, this whole line of approach of looking at distortion. It can help you compare not only voting rules that all work on the ranked ballots or on partially ranked ballots, but you can actually use this approach to optimize the design of the ballot in the first place. So here is kind of what our picture looked like with the ranked ballots. But if you have a different design for the ballot, in general, voters have these preferences. You have a certain design for your ballot. They answer those questions to convert their underlying preferences to whatever the ballot that you want them to fill out. So they fill that out. That is passed to the vote aggregation rule, and that selects the winner. And you can actually apply the distortion approach to optimize this whole process from start to end. So you can optimize the design of the ballot and the vote aggregation rule at the same time. And in fact, you have these different types of ballots like ranked ballots or top T ballots, but also something like range voting or approval ballots. You can compare all these different ballot formats using the same principled approach. So this is something that the axiomatic approach often doesn't allow us to do because you have to define different axioms for different types of inputs. Whereas here you can compare the different types of inputs on the same benchmark. But of course, you can't just look at the distortion of these different types of ballots. So what you can do is, for each ballot design, you can associate with it the most efficient way of aggregating the votes in that ballot design, and that is the lowest distortion that the ballot allows us to achieve. But it's not enough to just look at that, because the lowest distortion, the best ballot, to minimize the distortion, is the one that asks the voters to simply report their utility functions. And then you can get distortion 1. But of course, the reason we are not doing that is because this is cognitively very burdensome for the voters. So you have to kind of trade off the distortion with some kind of effort that the voters have to put in order to communicate the information to you, which we just take a very crude measure here and look at the number of bits of information that is communicated by the voters. So here we make some connection with sketching literature and streaming algorithms literature and communication complexity literature to derive the best bounds. Let me just directly show you these bounds here. So for selecting a committee of size k, here is what the ranked ballots gave you. So we were able to achieve this optimal distortion for a committee of size k, and ranked ballots elicit m log m bits of information. When you rank m candidates, you are providing m log m bits of information. But the optimal ballots, the optimal deterministic and randomized ballots, they achieve the following trade-off. For any distortion d, you need to ask m divided by kd bits of information if you want to ask deterministically chosen questions to the voters. And you achieve this, you need to elicit this many bits of information if you want to ask randomly chosen questions to the voters. And this is much, much better than what the ranked voting achieves. For example, if you want to achieve a square root m distortion, then really you only need to ask for square root m bits of information, even with deterministic ballots, as opposed to m log m bits of information. Right. I think, how much time do I have? 5 minutes? Yeah. All right, so the last thing that I want to show you is a consideration other than efficiency. So far I've been talking about maximizing social welfare and trying to approximate social welfare. But what if my goal is not maximize social welfare, but rather achieve some form of fairness? The high-level approach that this distortion literature takes is don't try to work with qualitative notions, rather try to work with quantitative notions that allow you to define what is the best voting rule. And so in our paper, we propose a very similar quantitative notion of fairness that can be applied to single winner voting rules. And to our knowledge, there are very few, if any, notions of fairness that can apply to single winner voting rules. Usually most notions of fairness apply when you are selecting a committee of voting rules, because that's when you can really define whether this committee really covers all the voters in the sense of like set cover or some kind of coverage problem. But this, for the single winner voting, we use a very well-known notion of fairness called proportional fairness, which Sid has worked on quite a bit. And proportional fairness of any outcome X on any given underlying information, this utility profile, is simply what is if you look at the best over all possible other distributions Y that you could have chosen, what's the average or the total change in the percentage utilities that happens when you go from X to Y? So for each voter, you look at the ratio between the utility for Y and the utility for X. So this could be 100% if X and Y are the same. It could be more than 100%, less than 100%. And you just average that across all the voters. And you ask how much this quantity is in the best case over all possible other Y. And a folklore result is that you can make this quantity equal to 1 by choosing the distribution that maximizes the Nash product of the utilities of the voters. I won't get into why. My main concern here is that I don't really know what this utility profile is. So what do? Well, I use a very similar approach. Given any preference profile, which gives me some partial information about the underlying utility profile, I just say, if I have to choose some outcome X based only on this partial information, in the worst case over all the underlying information that I'm not seeing, what is the proportional fairness objective that I can guarantee? And the lower here is better, so that's why we want to minimize. And what we show, first of all, is that the stable lottery rule continues to have this amazing number of square root m for the proportional fairness objective as well, but through a very different proof. But interestingly, here the stable lottery rule does not crush the competition. There is actually something that you can do better than the stable lottery rule. There is a different, efficient, randomized voting rule, again polynomial time computable, but much harder to describe, does not have any of the nice structure of the stable lottery rule, at least not to my eyes. But that rule achieves this log m proportional fairness, which is much better. And this is a slightly more intricate proof using a stronger form of the minimax theorem with some convex concave utility functions. And this is actually optimal. So you cannot get better than log m proportional fairness in the worst case given ranked ballots. All right. One last thing is that if you don't really buy proportional fairness as a nice notion for fairness, one thing that I can tell you is that it actually implies other nice notions of fairness that people have thought about in the literature. One of them is the core. And the core literally says the following. If you look at any X percentage subgroup of voters, any subgroup of voters that's X percentage of the total population, and if you let them allocate X percentage of the probability mass or of the available budget or whatever resource you are trying to divide, then they shouldn't be able to find a Pareto improvement. So any subgroup of voters shouldn't be able to allocate their proportional entitled share of the budget in order to find a Pareto improvement. And this should hold for any X. And there is a folklore result that any alpha value of proportional fairness implies alpha approximation in a certain sense of this core guarantee, which means that our result actually gives you a log m approximation of core. But for this weaker notion of the core, we actually don't know whether this log m is optimal. The only lower bound that we have is 2, so there is actually some interesting gap here that we can fill. If you still don't buy proportional fairness, there is another thing that proportional fairness implies, which is distortion, which is again welfare approximation, but not with respect to the utilitarian social welfare, but with respect to the Nash social welfare, which is the geometric mean of the utilities. So if I don't know these underlying utilities, but I want to try and approximate the geometric mean of the utilities as much as possible, what approximation can I get? Once again, there is a folklore result that says that if you get alpha value of proportional fairness, you can get alpha approximation of this Nash social welfare objective. Which means that we can get this log m approximation of the Nash social welfare objective. But here, the only lower bound that we can show is E, and we actually think that this should be the tight lower bound. We actually have an expression as a function of the number of candidates that converges to E when the number of candidates goes to infinity. And for 2 candidates, we can show that that expression is in fact the tight bound. So we think that the correct bound should be E, so there is some gap for improvement here. All right, so that's all I wanted to convey for our work. In terms of some future work, there is a related framework of metric distortion, where voters don't have utilities for the candidates, but they rather have costs for the candidates. And these are induced by some underlying metric space in which voters and candidates lie. And here, you don't want to try to approximate maximizing the sum of utilities of the voters. You want to try and approximate minimizing the sum of the costs of the voters, or rather pick the candidate that has the smallest total distance to all the voters. And it turns out that the best deterministic voting rule can achieve a 3 approximation, so it can always select a candidate that no matter what the underlying metric space is, its total distance to all the voters is no larger than 3 times the minimum possible. And I believe that Daniel actually gave a talk about this in the theory seminar last semester. For randomized rules, there was a recent improvement. Until now, people believed that the best distortion for randomized rule should be 2, but there was a very recent paper, actually December 2021, which showed that there is a lower bound that is slightly larger than 2, so 2 is not the right answer. And neither is 3. There is an open interval here. So somewhere between 2 and 3 is the right number, and this is a major open question in the field as well. But you can kind of take this further. You can ask, what if I don't want to select a single alternative? What if I want to select a committee of size k? We have some results for that. There is some interesting trichotomy here. You can, but also an open question is, what if you want to extend this framework to ballots other than ranked voting? What if you want to optimize the design of the ballot in the first place in this metric distortion framework? And what if you want to extend this framework to some other more complicated, more combinatorial models of voting, such as something called participatory budgeting? And then for ballot design, we use this kind of the number of bits of information that the voters convey as a very crude measure of the cognitive burden. But of course, a lot more research needs to be done, both from kind of psychology and HCI perspectives, to really understand what imposes the cognitive burden on the voters. There are also some intangible aspects of ballot design that we need to keep in mind. So a few years ago, I was talking to the Barcelona participatory budgeting team, and they were using something called knapsack votes, where they just tell each voter, if you had the entire budget of the city available for you, how would you allocate this budget between the different possible sectors or between the different possible projects? And even though this kind of theoretically we can show that this is a pretty bad ballot design, it doesn't really allow you to optimize, it doesn't actually give you any useful information for optimizing social welfare. They were very happy with this ballot format because it kind of teaches the voters the limitations of the available budget. The voter can kind of try to allocate that budget to different projects and realize that immediately as soon as they try to fill up 4 or 5 projects in their bucket, automatically the budget runs out. So these are some more psychological aspects that also need to be kept in mind. There are some other desiderata that you might want to combine with distortion. One of the very nice results in this literature is that you can actually get the optimal square root m distortion up to some log loss with truthfulness. So you can actually have a strategy proof voting rule that gets near optimal distortion, but it would be interesting to combine this with other axioms and some kind of explainability or interpretability. Yeah. And then this kind of approach of distortion, which is really just price of missing information, can be extended to problems beyond voting, like fair division, matching, collision formation, or more general graph problems, where really you want some more expressive input, but you are instead given some limited, less expressive input, and you are really just asking for the price of the missing information. Right? So that's it. Thank you everyone for your attention, and if there are any questions, I would be happy to take them. Yes.
So I'll propose something very anti-democratic. So to reduce the overall load, I mean, there is dependence on the number of voters in some computation, right?
Mm-hmm.
Obviously, that you have. But then you give a definition of utility that you're trying to optimize. So is there any investigation in terms of, like, depending on the distribution of these utility functions, can you sample from the voters in an appropriate way?
Yeah, so there are very kind of well-known results that any of these things that you want, you can just convert them to, by retaining very similar approximations of social welfare, you can just use standard Hofding bounds. You can just sample log n number of voters instead of all the n voters. You can just reach out to log n voters. In fact, not even log n voters, you can just reach out to log m voters, where m is the number of candidates. Sorry, m to the 5 log m or something like that, or m to the 5 log n. Sorry, log n is still there, but then there is some factor, polynomial factor of the number of candidates as well. And that's enough to get a pretty good estimation of the social welfare. So any of these things that you want to do, I mean, I haven't really checked whether the rules that come out of our work can be extended like this as well, but I'm pretty sure that they should be, it should be possible to extend them. It's just some kind of standard use of Hofding's inequality, but that would be a very nice thing to check as well. But yeah, it's something that I think would be useful again in non-political settings. In political settings, you don't want to tell some of the voters, no need to come in. I already pretty much know what your preferences are based on these log n voters that I've already sampled. You just stay home. No need to come in.
Be careful of that opinion. You're Canadian. So.
First you toss a coin, right?
Yes.
And then if it's one health, you don't ask anyone.
Yeah. So if the coin turns up tails, don't even need, nobody needs to come in. I just choose something at random. Any other questions?
A sort of obligatory question about, so I really like the stable rules, so the way you're using the linear, but do you know anything about the incentive properties of just stable selection rules? Like, are voters incentivized to report truthfully if they know that they're just using stable with some probability?
Yeah, I'm pretty sure that the answer to that is no. So what I do know is that the square root of m log m rule that the Boutillier et al. Designed, which is the harmonic score based rule, that rule is already strategy proof. So it actually, you can represent this as a mixture of unilaterals and duples, and you can actually show that this is strategy proof. So we know that you can get square root of m log m distortion while achieving strategy proofness. Whether you can get rid of that square root log m factor and actually get the square root m distortion with strategy proofness, I don't really know. Yeah, so but I am pretty sure that the stable lottery rule is probably not strategy proof. I mean, it seems more complicated than what you should be able to get using just unilaterals and duples. Oh yes.
So assume if you want to maximize your social welfare and so you build a function of candidates, assume you have a scenario where you have, like, on one side of the spectrum, like a candidate with maybe like 40% of the utility function. And then on the other side, you have two very similar candidates to get like 30% each. Then wouldn't that elect the one candidate that's like away from everyone and therefore like a minority candidate? Or
Yeah, so really great question. That if you want to go for social welfare maximization, let's say you know all the utility functions, and then there are these kind of two groups of voters that are almost indifferent between two candidates, and then a third group of voters, but they kind of break ties differently, and then a third group of voters who like a different candidate more. Once again, so the utilitarian social welfare is a measure that is susceptible to the kind of problems that you are talking about. It actually does not choose what we would think as the fair outcome. But proportional fairness is something that would actually give you the distribution, the kind of distribution that you are aiming for. So this is where, if you care about fairness or some kind of proportional representation of the population's preferences in the distribution over alternatives that you are computing, then you want to actually go for proportional fairness approximation and not social welfare approximation.
In that case, that would not involve any strategizing, right, of just like not actually putting your real preferences.
I mean, so again, like even the proportional fairness rule, I'm pretty sure it's not strategy proof. But it may not be susceptible to the obvious kind of strategizing, such as just splitting the votes or things like that, or not splitting the votes.
Online?
Yeah, I don't think so. Any people have any questions on Zoom?
So then maybe one semi-adversarial question. So you sort of started off motivating utilitarian, warning you about, but okay. So you started off motivating this rule saying the axiomatic rules kind of end up not giving a unique rule, and therefore that's not a great idea. But it feels like they're not giving unique rules here either. They're sort of giving, so like, given what you know now, like what's your justification for suggesting?
Right. So when you say that we are not even getting a unique rule here, you mean that there is one rule if you want to maximize social welfare, there is another rule if you want to aim for proportional fairness. Is that what you're talking about?
Or even just that when, yes, there's a unique rule, like anytime we write an optimization problem, it's very complicated and unique, but we're not giving a simple rule.
Oh, simple, yes. Yeah, so simplicity is kind of one of those things actually right here that's very interesting. I think that there are domains of group decision making where simplicity is not necessarily as desired as in the political context. So for example, if a group of friends are making a decision on where to go for lunch, if there is an app where they can just kind of rank the different restaurants and the app can quickly tell them, okay, today you go to Banfi, tomorrow you go to Coco, the next day you go to Sangam, then that kind of an app would be good enough for that application. Even if the group doesn't really know how the app is making decision, as long as they use this app for a month and they are pretty happy with how the app is making decisions. So there are some domains where simplicity is not necessarily desired, and in those domains my claim is that a rule that actually gets at least better approximation of social welfare, and therefore likely better social welfare in the long run, that kind of rule should be used. Which is why I'm never pitching any of these rules for the political election context. I think David, did you ask me or maybe someone asked me yesterday in my meeting with them that if like today you were made like the czar of United States of America and you had to decide which voting rule will be used for choosing the president, which voting rule would you use? And I would not use any of, first of all, I would not use any probabilistic voting rule. I would use a deterministic voting rule, and I would probably use the same system that is used by the French presidential election system with the two-stage instant runoff voting. So, there are a lot of advantages, but I think when you talk about political systems, there are a lot of factors other than social welfare or fairness or any of these technical measures that matter a lot more than these technical measures. So that's why whenever I talk about voting, the first thing that I try to do is to get the audience stop thinking about political elections and start thinking about a lot of other decision-making contexts where we can actually make a difference. I don't think that it's feasible to change how the political elections work in a very, very significant manner. Say, for example, going from simple voting rules to these automated voting rules that you don't really know how or don't really understand how they work, but you have some trust, if you trust the math, that they are making optimal decisions in the long run. I don't think that that's a feasible change to implement in the next kind of foreseeable future in the political context, but in other contexts it may be feasible.
I don't know if this is off topic, but I guess compared to the French election system, like, why would you say, or like, why would you think, like, for example, it's better than, say, a ranked choice voting system, the way it was generated in New York City for mayoral elections?
Oh, the two-stage instant runoff voting. Why is it better than ranked choice voting? Yes, after the New York City did this, the ranked choice voting, a lot of interesting analysis came out, and I think some of them very compellingly showed that a non-negligible fraction of the voters don't even understand how to submit ranked choice votes. They ended up making an error where, I mean, one of the reasons is that if you have a UI, if you have like an interface where you can drag and drop different options in the ranking order, then I think it's very easy to submit ranked choice votes. But what ends up happening is that in practice, people rely on paper ballots. And on paper ballots, the kind of the only reasonable way of doing ranked choice votes is something like this. And here, any valid ballot has a constraint that there should be a unique box filled in every row and every column. There is an assignment problem constraint happening in this ballot, which I think is very difficult for many voters to understand. So there was an interesting analysis. I think something like 5% of the votes, something that's very non-negligible, they were thrown out because these ballots were not valid. So I think ranked choice voting is still something that's kind of beyond our reach, at least for the next foreseeable future. I think that's something that's simpler than that. Something that's slightly more expressive than plurality, but not as expressive as ranked choice voting, which is this kind of two-stage process, may be doable. Yes?
I guess, yeah, sorry. My main concern of, for example, the French voting system is, well, last week there were the first round elections, there's basically three candidates that got 20% to 30% right. So it's just like one candidate basically gets knocked out, even though they were almost equivalent to the other two. So
yeah.
That it's going to be exactly two candidates, right?
That's true, and so that, I mean, the one thing about this like two-stage system is that it's not the optimal solution to anything that you are trying to optimize. If you are trying to optimize something, you either go all the way to an M-stage system, which is the single transferable vote, or you stay on the other extreme of simplicity with plurality elections, right? I think it's just more about kind of finding a practical trade-off. I do agree that it has that problem. It tries to resolve that problem, but doesn't go all the way through. But I think that's kind of where I think the practical trade-off lies. But I may be wrong. And I know that many regions are implementing ranked choice voting in the full form. So.
Okay, I think this is a good time to stop. So let's thank Nisarg again.
Thank you so much for coming.